Hey, everybody. Welcome back. We're going to start covering chapter 7. And so, like we said previously, chapters 4, 5, and 6, along with chapter 7, are what we would consider very heavy on the math. Chapter 7 here, we're going to look at thermochemistry. We are going to talk about enthalpy, delta H. When you get into Gen Chem 2, you'll be able to talk about delta S and delta G, which gives free energy. But we're just going to look at one part of that here. You might be looking at the picture on your slide and thinking, uh-oh. I just want to, I like presenting this picture for two reasons. One, it's just a pretty funny picture. And for two, it was presented to me when I was a general chemistry student. Now, what the professor did in my class was he put our names, like the class's mascot, if you will, over the guy, and he put their names, the professor's names, over the buzzards. I am not going to do that, right? Sometimes in this chapter, you might feel like that guy going through the desert, but I want to give you some rules and some tips, or not some rules, but some tips to get you through this section on thermochemistry, because it is a little bit because it combines some math that we need, as well as some conceptual things that we really have to think about. And so the first one is obviously watch the lectures. Normally my first tip is come to class, but obviously we're not coming to class, and so just watch the lectures. Number two is have a spotter, right? Have a classmate, have a person that you could email or message, or have somebody else who's taken the class that you can message when you're struggling with it, that you could go to a peer first, and then you can come to me, right? I'm always here to answer any of the questions that you guys might have. The third one is work the problems, right? Work the problems and then ask questions that you guys might have that come from the problems. But you got to do the homework. You got to work it. You got to actually put what we're learning into practice. And then the last one is think. Some of the things, it is going to take a lot of us, or a lot of stuff. We're going to have to think about a lot of stuff, but we're actually going to have to think about it, and we're going to have to maybe slow down a little bit to fully grasp the full picture. And so let's go ahead and jump into thermochemistry. And so what are we talking about in thermochemistry? Well, we're talking about energy, right? And what is energy? Energy is the capacity to do work. Now, not just any work, but useful work. What is work? A work is a force acting through distance, right? So we saw pressure is force acting over an area. Here we're looking at force acting through a distance. Work we'll see is equal to F times D. And then there's also heat, right? So what is heat? Heat is just the flow of energy through temperature differences, usually from warmer to cooler, right? So if we use the example, and we'll use it again and again and again. If a person is naturally cold or cool, that you touch their arm, your hand is now going to be cool and their arm is going to be warm, right? So that's the natural flow of heat. Energy, it takes energy to break and form chemical bonds. Sometimes energy is released when we form chemical bonds. There's actually two types of energy that we're really going to focus on here in this class. We have kinetic energy, right? So energy is capacity to do work. We can break energy into two things. One is kinetic energy, energy that is associated with the motion of an object. You can imagine a roller coaster going down, a decline down the hill. That would be kinetic energy. Another type of kinetic energy, right? So we have kinetic energy, and then there's a subtype of kinetic energy that we can call thermal energy, right? This is the heat transfer we're talking about. This is the energy associated with the temperature of an object. Now, let's think about this, right? Because this is where we start to think about things. Why would thermal energy be characterized under kinetic energy? Because what is temperature? What is that? What is temperature? You're right. It is the movement of atoms or molecules, right? And so if something is associated with temperature, it's going to be associated with movement. That's kinetic energy. Potential energy is the energy associated with a position or composition of an object, right? So let's take our roller coaster example. On the downhill, it's exhibiting kinetic energy. Well, roller coasters climb and then just stop or slow down at the very top. that roller coaster car is exhibiting potential energy. It has the potential to do work. It has the potential to do whatever. And so it's just sitting up there. And then what happens is it then gets transformed into kinetic energy as it goes down the hill. Chemical energy is a type of potential energy. It's associated with the potential energy associated with the relative positions of electrons and neutrons. This is where we get our food, right? This is why we eat. Within that food, there is stored chemical energy, and our body is able to transfer that chemical energy into kinetic energy for us to do something with it. Energy, just like we saw with mass, cannot be created or destroyed. This is known as the law of conservation of energy. This is the first law of we'll talk a little bit about the first law of thermodynamics in a minute. It has very similar implications. So how can we define what happens to energy, right? Because if energy can't be lost or destroyed but being transformed, that's how we can define what happens. Is we transfer energy from one system to another. As the lady there with the ball, right? We have potential energy, and then she lets go of the ball. It gets transformed into kinetic energy. You see that in your car, right? The gas that we put into our automobile is potential energy. We start the car. It combusts. It burns. It gets the energy from that for the car to go. And so let's talk about kinetic energy for a little bit. Kinetic energy is defined as the mass of an object moving at some volume, right? So kinetic energy is equal to, which is that KE was equal to 1/2 m mass in kilograms times the velocity of something, which is meters per second. Now, what we can do is we then have that unit of that kinetic energy, usually for the SI is the joule. Now, this will come back. We'll just keep this in mind, right? That we're not going to be too picky. Like, I'm not going to say, okay, how much kinetic energy does this thing have, right? We're not a physics class. This is physics, but we're not going to do any of these specific calculations, but we do need to notice the joule, right? That the kilogram and meters per second squared, those two things together equal the joule. And the reason why we have to notice that is because it will come back. Now, the SI unit for energy, pardon me while I come off camera for a minute, the SI unit for energy is joule. However, we can use a calorie, right? A calorie is the amount of energy required to raise the temperature of 1 gram of water 1 degree Celsius. 1 calorie is 4.184 joules, right? So 1 lowercase c calorie is 4.184 joules. This is important. Notice I say lowercase calorie because there is a difference between a lowercase calorie or lowercase c calorie and a capitalized C calorie. And if you look, so here I just have a jar of peanut butter in my office. I don't know how clear that picture is, but if you look at the calories, right, that is an uppercase C calorie. Food calories are usually uppercase C, which means that is equivalent to 1,000 calories. So in that peanut butter for a serving, it's 108,000 lowercase c calories, right, or 180 kilocalories. And we just know this. We just just be careful when we're talking about lowercase c, uppercase C. It'll be pretty explicit when we talk about it. Energies, just to let you know, mowing the lawn takes about 30 kilojoules per minute to mow it, about 10 minutes. If you're digging in the garden, digging some soil, it's about 33 kilojoules per minute. Jogging, about 6 miles per hour. It's about 40 to 48 minutes, or 40 to 48 kilojoules per minute for about 8 minutes, right? And so so we need a lot of food, right? That's why there's so much food, so many calories in our food, is so that we can then put them to work. Now, what's important and what we're going to see is we're going to talk about thermodynamics. right? We're thermochemistry, thermodynamics, very similar things. And so what we're going to see is the first law of thermodynamics, which just states the total energy of the universe is constant, right? Again, law of conservation of energy. You can't, the energy is just transformed. You cannot get energy without the input of energy. You can't just snap my fingers and boom, energy is made. What we're going to see is we're going to start talking about this concept of system and surroundings, right? Because the energy has to be transferred from one thing to another. And so what we're going to look at is what's known as the internal energy of a system, right? This is the sum of kinetic and potential energy that a system has that composes that system. Now, it is known as a state function, and a state function is very important. We're going to see why in the next couple slides, but a state function is important is because the state function doesn't care the pathway you get from point A to point B. Like I usually do a demonstration when we're in the class. Like if I were to start in the back corner of my office and walk directly across my office to the other corner, or if I started in the same corner, but then I kind of meandered around and walked and slipped and fell and got up and then finally landed in the same corner where I ended before. The state function just says, I care about where you began and where you ended. I don't care what happens in between. And so we're going to start seeing this, and we're going to put a delta in front of these things. And whenever we see a delta, that means it's a state function. All we care about is the final point and the initial point. And that's it. And so what we see, and I'm going to go ahead and just share the board and go to the board real quick, just at this point to show you the internal energy. So let's go ahead and I'm going to just show you the equation for the internal energy of a system and why we just care about that it's a state function, because it would be really hard for us to do this kind of stuff in the absence of being a state function. And so what we have is the internal energy of a system, E. Well, what we're going to do is turn it into a state function, delta E of the system, right? We're going to start seeing these things because they're going to define what we're talking about. And that is going to equal the energy final minus the energy initial, right? The energy of the final state of the system minus the energy of the initial state of the system. Now, I want you guys to think about how that would relate to a chemical reaction, because that's what we're going to talk about. We're going to talk about chemical reactions. What is the final state of a chemical reaction? Exactly. It is the products. What is the initial state of a chemical reaction? Exactly. It's the reactants. And so what we can see is the internal energy of a chemical reaction is E products minus E reactants. And so let's go and flip the camera back around. All right, so that's a state function, and that's the internal energy. So how can we calculate internal energy change? Well, before we can start doing a lot of these calculations, and they're all based on E products minus E reactants, right? That, because again, we're talking about this. What we need to do is we need to talk about what is a system and what is the surroundings. And really, a system and a surrounding is arbitrary, however you define it, but there has to be a system and there has to be a surroundings. And so what we see here is the energy flow from a system to a surrounding and from a surrounding to a system. I'm just going to let you look at this a little bit. I'm going to actually I'm going to go to the board just so that we can see this in a little bit more detail. Because again, this is the conceptual things that we have to know now before we really start getting into the math. And so the first part, we're just really going to deal with just the conceptual. The next part, or probably the next two parts, is we'll really just focus in using on the concepts with the math of the chapter. So let's go ahead and let me go back to the board. And so let's go ahead and look at this in just a slightly different way. Or at least maybe let me explain it in a slightly different ways. And what we're going to see is that the signs of the numbers, no, I don't want to put that up there. The signs are very, very, very important. And so what do I mean by that? Well, let's have a system and let's have a surrounding. Right? So what we can say is, and I'll give you guys some practice problems on these. And you guys will practice this too, just to let you guys know on your quiz about systems and surroundings. But let's just say a system is a chemical reaction, right? And the surrounding is the beaker. Or, you know, the air surrounding it, or something, you know, we can just, or the liquid surrounding the actual, I mean, there's a variety of different ways we can define these. If we have the energy flow going this way, the energy flow, let's think about this. The energy is going from the system to the surrounding. What would be the sign of the delta E of the system? And what would be the sign of the delta E of the surroundings? Now, let's think about this just like a bank account, right? Let's think about this like a bank account. When you make a withdrawal from a bank account, what is the sign that's usually associated with it? And that is a negative sign. You are correct. When you make a deposit into a bank account, what sign is usually associated with it? Exactly, a positive. When you see the system negative and the surrounding positive, right, where the energy flow is going from system to surroundings, it is exothermic. Exothermic. The energy of the reactants is greater than the energy of the products. Now, let's think about this. What happens if we, let me find a different color marker. What happens if we transfer the energy the opposite direction? What happens if we go this way? What's going to be the sign of delta E system and delta E surrounding? Exactly. They're just going to be switched, right? Because we're making a withdrawal from the surrounding into the system. The energy of the products in this case will be higher or greater than the energy of the reactants. And so what will happen is this is known as endothermic, right? That one would be cold to the touch. If you've ever used an ice pack, one of those ice packs where you break it up and then it gets immediately cool, that is what happens. So what relationship can we see from here? What's the relationship that we can see from here? Is that delta E of the system is equal to negative delta E of the surrounding, right? Because when delta, and it has to be, delta E of the system is negative, delta E of the surrounding is positive. Delta E of the system is positive, delta E is of the surrounding is negative, right? And so there is that inverse relationship. And now, so what we're going to do, and I'm just going to show you the equation on the board, and then we'll talk about it on the PowerPoint slide. But I just want to go ahead and draw it up here. Is that the internal energy of a system, right? We talked about this, and in our definition, we said it's the total amount of work, which we're going to denote with a W, plus heat. Right? All the potential and kinetic energy of a system is going to equal the total energy of that system, internal energy of that system. And so let's go ahead and look at these two things, the Q and W, as the last thing that we'll probably get to look at on this part of this chapter. Switch the key. Okay. All right. So heat and work, going from system to surrounding, surrounding to system. What we see is a little table where the plus and minus, just like we saw before this, and we always define it by the system, right? We always define it by the system. And so this is why we have to know what the system is. And the system can really be anything that you define it as long as you are consistent. Now, we talked about energy, right? Delta E is a state function. What do we not see in Q or W? That's exactly right. We don't see a delta in front of the Q. We don't see a delta in front of the W. And so those are not state functions, which means the journey does matter. And one of the things that we're going to do is we're going to look at see how we can calculate heat transfer, how we can calculate work a little bit in these different equations. And so I'm going to leave you with this, right? So we're talking. So signs are very important. The system is very important. The surroundings are very important. So let's talk about. We're going to start talking about heat next in the next part, but I just want you to just look at this, look at the equation. We're going to start looking at this in a little bit more detail and actually figuring out what that means.